Hi students, welcome to Science Extension and Module 3, the Data, Evidence and Decisions. In this video, we're going to talk a little bit about bias in practical investigations. What you need to be able to do is to apply appropriate performance measures to the statistical analysis of quantitative data sets obtained from conducting relevant practical investigations, including but not limited to bias. So what we're looking at here are representative samples. We've talked previously about the fact that it's very difficult for you to be able to get the entire population of a particular variable that you're interested in. And so usually what we have to do is we have to sample. We take a small sample of a wider population and then we analyze that to see that hopefully the conclusions that we can draw from that sample will be representative of that wider population. But in order for us to do that, or in order for us to have our conclusions that are actually going to stand up to rigorous testing and critique, is that we need to make sure that we don't have biased samples. Now, bias can enter two ways, either deliberately because there is a particular slant that you wish to take in your experiment and you're actually being influenced in terms of both the data you collect and the conclusions that you are drawing on the basis of that bias, or sometimes it can be unknowing. We all have a social cultural background. We all have certain ways that we've been brought up. We have certain ethics and morals, and these will enter into pretty much everything we do anyway. What we need to make sure that we do is to be aware of any biases that we may have and to try as much as possible to minimize their impact in the experimental work that we do. Now, researchers may have reasons why they deliberately select a particular subset of a population. Sometimes we will just open a particular survey to anyone who sees a link, or to people that we know, or to people that are sharing similar social media platforms. And so therefore, the populations that we select may have some bias anyway, particularly in that form of self-selection. But we just need to make sure that there is validity in the procedures that we've carried out and in the conclusions that we can draw from our data. So we don't want to be in a situation where we're justifying an invalid result for some personal or commercial gain. You don't have to scratch too hard to find some really good examples of bias in science. And that's a sad thing, but it's true. One of the most significant examples, I guess, occurred through a period of time where smoking was very, very popular social activity, and increasing amounts of evidence were becoming available that were not only identifying a negative health impact of smoking on smokers, but also on other people who were around them, that idea of passive smoking. And so therefore, when you look through some different material, you can get a sense of how some of this bias was being played out in both scientific journals and through, I guess, more broad public discussion. So this is an abstract from one particular paper from Brandt in 2012, which is called Inventing Conflicts of Interest, A History of Tobacco Industry Tactics. And this is just the abstract. Remember, when we're talking about abstracts are always a good place to look because they provide a nice little summary of what's going to be in the paper. It tells you a little bit about what you're going to read about. And it also means that rather than reading the entire paper, if you feel like it's not relevant to your study or not something that you're interested in, you can just read abstracts and move on. However, if you do read an abstract and think that's really interesting or that's really relevant to what it is that I'm looking at, then you can go and get the whole paper and read it in a bit more detail. So this abstract tells us this: confronted by compelling peer-reviewed scientific evidence of the harms of smoking, the tobacco industry beginning in the 1950s used sophisticated public relations approaches to undermine and distort the emerging science. The industry campaign worked to create a scientific controversy through a program that depended on the creation of industry academic conflicts of interest. This strategy of producing scientific uncertainty undercut public health efforts and regulatory interventions designed to reduce the harms of smoking. A number of industries have subsequently followed this approach to disrupting normative science. Claims of scientific uncertainty and lack of proof also lead to the assertion of individual responsibility for industrially produced health risks. So this is giving us a really nice introduction to that idea of bias in science, and also some of the ways that scientists, or even just members of the public or industry, are going to use their own internal bias, whether that's personal or professional or possibly even both, to read, interpret, and discuss different types of scientific experiments and findings. What does that mean for us? Well, bias may refer to a systematic error resulting in measurements consistently being out in the same direction by the same amount. So an example of bias is parallax error. Now, we could regard that as a systematic error and it's a human error and you're not reading things properly. But maybe there's a reason why you are consistently doing this sort of thing. Now, this could just be an example of what we called before that unintentional bias, something that is making a difference to your results, but something that's just really about poor technique, or maybe you haven't been taught the correct technique and so you're using it incorrectly. But bias, I guess, is more concerning when we allow it to creep into the methodology, when we change what we're going to do because of an expected finding. Or we cherry pick our data, we collect data that is going to be more likely to support our point of view. Or when we process the data, this is particularly important when we're doing data cleansing, which we talk about next, and the identification of outliers. Sometimes those outliers are there and they need to be commented on, and if we just eliminate them in order to produce a nicer statistical value, for example, then we may be obscuring some very important part of our scientific research. Bias can also be part of our analysis of data. We can look at certain, and this has obviously happened a lot in the history of science, where people have looked at the same set of data and come to different conclusions, maybe small differences, maybe significant differences, and perhaps those differences have related to the sort of things that I wanted to see in the data, and so therefore I was seeing those whether or not they were objectively there or not. And even in the final presentation of data, it's important to make sure that you can justify all of your conclusions on the evidence that you have, that you're not drawing or extending some of the conclusions that you're drawing on the basis of your own personal views that are not actually supported by the evidence that you've collected. More recent example of bias, and covered beautifully in Dr. Karl's little book of Climate Change Science, is climate change. It's obviously one of those emotive issues. You don't have to go very far to find arguments about all of these sorts of things, and even the way that they're couched, such as a question around, do you believe in climate science? And in science, what we're looking at is evidence. We're collecting data and we're looking at evidence, and we're seeing how the evidence supports the hypothesis or supports the position that we have taken, or maybe contradicts the position that we've taken. Dr. Karl's been on about this for some time before he wrote this book, and it's only a small book. It is a little book, and it's a really interesting one to have a read of, even if you're just interested in climate change science and you're not interested necessarily in bias in science or bias in reporting, but it is a good example of both. Dr. Karl says, I'm back with the controversial topic of the so-called pause in global warming. Some parts of the news media incorrectly claim that the climate is no longer warming, but is actually cooling. They get to this conclusion by everything from cherry-picking the data all the way up to telling big, fat fibs. By way of complete contrast, early in 2014, the two most august scientific institutions in the United Kingdom and the USA issued a joint report entitled Climate Change Evidence and Causes. These two bodies, the Royal Society, that's the English one, and the US National Academy of Sciences, warned that climate change is more certain than ever. Their accurate data shows that the climate, as measured by surface temperature of air and water, is still getting hotter. But this average global temperature is not the only measure of climate change. There are other indicators that inform us about the state of global climate. Just as an abstract gives you a little bit of an overview of what's going to be in a paper, sometimes some of these popular reports in the media can give you a little inkling about the position that a scientist may take, and may even inspire you to go and read more of their work to see what it is that they're actually talking about. Dr. Karl's little book is a very good one for drawing out the arguments around each of these claims that he makes around the different attitudes towards climate science, and also, most importantly, a lot of the evidence that he uses in support of his argument. Sometimes science will throw up controversies, and that's no problem. One of the things that's rich about science is the ability to discuss, to critique, to repeat other people's experiments, and then to have robust discussions around the results of experiments and what they may mean. But it's very, very important that we are always aware of the potential for bias to enter at any stage in our scientific research. Thanks for watching.